press the bell icon on the YouTube app and never miss another update.
Now in the previous class, we have discussed about two important things. One, graphical representation of the displacement of a particle executing simple harmonic motion, right, against time, and we obtain a curve, resulting curve for one complete oscillation or one complete simple harmonic motion, right, called a sinusoidal curve, right. The nature of the curve is sinusoidal curve, right, just like exponential curve, right, just like a straight curve, etc. It is a sinusoidal curve, right, and we have plotted the graph with the help of both uniform circular motion and simple harmonic motion of foot of the perpendicular along the diameter y dash of the circle, right. Now we have also discussed about the term phase of a vibrating particle, right. That is very important. Once again we will recall that phase, right. Again I am repeating, the term phase is very important, and the phase difference is another term we are using in the same context, right, and that phase difference is very important in understanding, right, the beats, formation of beats in the case of sound, formation of stationary waves, interference of light, diffraction of light, and in understanding alternate current circuits, where we are going to use the word, right, phase difference. You might have heard that there are AC in AC, three-phase current, two-phase current, and single-phase current, like that, right. So therefore it is very important to understand the concept of phase, right. Now, phase of a vibrating particle at any instant of time is the state of vibration of the particle at that instant of time, right. Now, phase or state of vibration of a vibrating particle at any instant of time, right, gives both position of the particle from the mean position and direction of motion of the particle, right, from the mean position, right, at that instant of time. So whenever we are locating the position of the particle executing simple harmonic motion, right, it is important to locate the position as well as the direction of motion, right. It is because in one complete oscillation or simple harmonic motion, right, it is associated with the four different directions, right. We can take basically two directions, positive side and negative side, right. Positive side towards the right side of mean position, and negative right side is towards left of the mean position, right, or positive sides above the mean position, right, negative side below the mean position. When we take in positive direction, right, one moving away from the mean position in positive direction, two moving towards the mean position in positive direction, three moving away from the mean position, right, in negative direction, four moving towards the mean position in negative direction. So there are four different directions. Therefore, right, we have to specify both position and the direction of motion. The quantity which representing both position and the direction of motion of a vibrating particle or a particle executing simple harmonic motion is called phase, right? And phase is also termed as the state of vibration of a particle, right? Now it is clear. Phase gives position, right, of the particle from the mean position and the direction of the motion of the particle at any instant of time. Now how to measure the phase? So phase can be measured in two ways. In terms of fraction of time period, that is the time taken to complete one oscillation or vibration, and in terms of fraction of 2 pi, where 2 pi is the angular displacement of the particle for one complete rotation. When the time taken by the particle is equal to period, then the particle completes an angular displacement of 2 pi, right? Now we have displacement equation. Y is equal to A sin omega t, right? In the term A sin omega t, in this equation, the term omega t represents phase, right? It represents phase. Therefore, now phase of a vibrating particle at time t is given by phi. It is the standard symbol for both phase and phase difference, right? Phi is equal to omega t. Where what is omega? It is the angular velocity or angular frequency. We know that in terms of time period, omega t, omega is equal to 2 pi by t into t, right? So phase of a vibrating particle is not a constant quantity, right? As the time changes, the value of phase also changes, the direction of motion also changes, right? Now this is the phase of a vibrating particle at any instant of time t, right? So therefore this expression involves both 2 pi and t, right? So phase can be expressed as a fraction of time period t or as a fraction of 2 pi, right? Now phase of a vibrating particle at any instant of time is defined as the fraction of time period or the fraction of angle 2 pi that has elapsed since the particle has, right, crossed its mean position in positive direction, right? So the phase phi is equal to omega t, right? Now let us consider graphical representation of a vibrating particle. The particle is at O and it has two extreme positions, M and N. The 4 arrow marks indicates 4 different directions in one complete vibration. Now Right. Now, we'll represent the motion in terms of displacement time graph. Right. Now, this is the origin O representing the mean position, and time is taken along x-axis. The displacement y is taken along the right y-axis. Above the mean position, y is positive. Below the mean position, y is negative. Right. Now, when the particle is at O, right, now we will obtain a curve like that. This in graph, I will represent it by B, right, that represents the position right N in the figure oscillation. Now then, when the particle comes to O, I will represent it by C in the graph. That C corresponds to again O after completion of half oscillation. Now again, when the particle moves from right O to M, the direction changes. Now the particle right is moving to right M. This I will represent it by D. Actually, this is M in the figure, right? Now, right. Now, when particle moves from right M to 0, right, now we will obtain a curve. Say D, E, right, now again that represents O, right. So here for your convenience, C is equal to E is equal to O according to this figure, right. Here we have the directions C 1, 2, 3, 4, right, 4 directions 1, 2, 3 and 4 directions, right. Now, so whenever we take the phase of particle at O, that is at time t is equal to 0, right. I will take the phase at O when time t is equal to 0. This is equal to, we have 2 pi by t, right, into t. The value of t is 0 into 0, right. That means, right, phi naught is equal to 0. The phase of the particle at point O is 0. At the point 4, phase is, we can take, it is 0, right. Now, right, and when I put this phi naught, omega t is equal to 0, then we have the displacement y is equal to 0, right. When we use it in the equation, y is equal to a sine 2 pi by t into t in that equation, right. When we substitute t is equal to 0, now it becomes sine 0, y is equal to 0. Now similarly, phase at B, I will take directly, phase at B is equal to, right, when the particle comes to this point, right, the time taken is equal to T by 4, right. That means now 2 pi by T into T by 4. That implies the phase at B is equal to, right, T get cancelled, that we get pi by 2, right. So in terms of fraction of time period, the phase of a particle at B is T by 4, or in terms of fraction of the angle 2 pi, right, it is pi by 2. Now here we get, so phi b is equal to pi by 2, this is YO, we will take displacement at position O. Now YB is equal to, right, plus A. So sin pi by 2 is equal to plus 1, y is equal to plus A. This is representing the plus A. Now we have phi C is equal to phase at C. The time taken is at this point, this is T by 2. Therefore, it is 2 pi by T into T by 2. So 2 get cancelled, T get cancelled. Therefore, phase at C is equal to pi. So phase at C is either T by 2 or it is pi. When I substitute 2 pi into T, right, is equal to pi, right, then I will get the position at C, right, YC is equal to 0. At C, the displacement is 0. Now the phase at D is equal to 2 pi by T into, now here the time taken is 3 T by 4, right. This is substituting here, 3 T by 4 we get. Here it is, right, what? 3 T by 4. 3 T by 4 we get. So phi at D is equal to 2 get cancelled, 3 pi by 2, right. So in terms of angle, the phase is 3 pi by 2 at position D. Now here the displacement YD is equal to, now this term in this equation becomes 3 pi by 2, 270 degree, sin 270 degree is equal to minus 1. Now that implies YD is equal to minus A. That is the maximum displacement in negative direction, right. Now similarly, the phase of the particle at E. Now here the time taken is T at that point. So 2 pi by T into T, right, that implies phase at E is equal to 2 pi. The phase at E is equal to 2 pi, right? Therefore, it is also represented by 2 pi. Now, when we substitute the 2 pi here, right, then we will get YE is equal to 0, because sine 2 pi is equal to sine 360 degree is equal to 0, right? Is this clear? Now, this is how we can represent. Now, suppose if the particle continues to execute vibration, right, then we will get the graph like that. Here phase is 0, here it is pi, here it is 2 pi, here it is 3 pi, here it is 4 pi, here it is 5 pi, here it is 6 pi, here this is 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, and so on. That means the phase is 2 pi means the position of the particle is at mean position, y is equal to 0, but it has completed one oscillation. Now the phase is 3 pi means now pi by 2, pi, 3 pi by 2, 2 pi. Again it goes here and comes back, plus pi, 3 pi. So, phase is 3 pi means the particle is at mean position, that is displacement is equal to 0, but it has completed 1.5 oscillation, right? One complete oscillation and 1/2 oscillation in positive direction. The phase is 4 pi means the position of the particle is at mean position, right? Displacement is 0, but it has completed 2 oscillation. Here oscillation is yet to start. Here 1 oscillation is completed, here 2 oscillation is completed, here 3 oscillation is completed, here 4 oscillation is completed, right? When it completes 4 oscillations, right, its phase is said to be 8, right, pi, right? And now here this particle phase at O 0, phase at N, right, pi by 2, again phase at O pi, right? Position is same, but see it here. When phase is 0, the position is mean position, but it starts moving in positive direction. When phase is pi, right, then the particle is again in mean position, but it starts moving in downward direction, right? That is away from the mean position. Now at M here it is 3 pi by 2. The phase is 3 pi by 2 means the particle is in extreme position in a negative direction and it has a tendency to move, right, in a upward direction, that is towards the mean position, right? This is how the phase of a vibrating particle at any instant of time represents both position and direction of it. Suppose phase is 120 degree. The particle is somewhere between OB, moving in, right, positive direction away from mean position. Suppose here 120 degree phase, that means the particle is somewhere between B and C, right, moving towards the mean position in positive direction. Now 180, say phase is 200 degree, then, right, now the phase can also be expressed in radian as well as, right, the degree. Here it is 0 degree, 90 degree, 180 degree, 270 degree, 360 degree. Now when it is 200 means The position is somewhere between C and D, but moving away from mean position in a negative side. So this is 270. Say phase of a particle is 300 degree. Then the particle is somewhere between D and E, but moving towards the mean position in a negative direction, right? So between 0 to 360 degree, between 0 to 2 pi radian, right, we can find both position of the particle, that is displacement, and also the direction of motion, right. So since the motion involves 4 different directions in one simple harmonic motion, right, the phase becomes very important here, right. When phase of the particle at O is 0, phase of the particle at C is pi. These two positions have different phase, but here the phase is pi, the phase is 0, the phase difference between C and O is pi minus 0, that is 0, but at this stage we cannot take the phase difference because there is only one particle which is oscillating or vibrating, just like a simple pendulum. When we held a vibrating tuning fork in air, the air particle began to execute simple harmonic motion, producing the waves called sound waves. When sound waves are propagating, large number of particles are executing simple harmonic motion or vibration, right. In that case, right, we need to take the phase difference, but when we are considering oscillation or vibration of a single particle, generally we won't consider phase difference, but we consider what? Phase. If we understand the phase clearly, then we can understand the concept of phase difference in waves, and we can easily understand superposition of waves, right. The superposition of waves plays a very important role, right, in our day to day life. For example, we can hear beats. Now, let us consider another point. We will take it as note that here we are discussing a term called epoch or initial phase. Right. Final. Suppose when the particle is executing simple harmonic motion and it is understood in terms of circular motion. When the particle is at B at time t is equal to 0, right, then we have the position of the particle at time t, then this is theta, right, then this theta is equal to omega t here if the particle is moving with angular velocity, right. And again, when we take the case of a simple pendulum, this is the mean position of the simple pendulum, equilibrium position when it is at rest. Now, when it moves to position O to position P in time t, now this is the angle theta, and this is displacement y. Here this is displacement y. So here also theta is equal to omega t, and we have equation y is equal to a sin omega t. Now that so far we have discussed. This is the equation of simple harmonic motion, gives displacement at any instant of time t. But there is some case here. Again here, this is O, this is position of particle B at time t is equal to say, generally we have taken. So instead of taking that time, when we take the particle P at some position, right, with an angle, right, this is some theta we say, don't say theta, I will say at some angle, say phi naught, from the mean position. Now the particle, right, at any instant of time, right, p of t, right, now the particle is at p at time t, then this angle covered is equal to omega t. See this here, theta is equal to omega t. But right, from the mean position, this angle is, right, theta, right. Now this theta is equal to omega t plus phi naught, right. So here phi naught is called initial phase, right. That means the phase, when we consider the particle is not in its mean position, it has already covered some displacement, right. At that position we are taking the time t is equal to 0, then initial phase difference, right, is not equal to 0, it has some value. Again, when we take the case of a simple pendulum, this is at mean position. Suppose the particle is Bob is at position P when we take time t is equal to 0, right? So it has already, right, has some angular displacement phi naught when we take phi is equal to, right, when we take time t is equal to 0. Now after some time t, it moves to another position p of t in a time interval t. Now this angle is omega t. Now the angular displacement from p of 0 to p of t is omega t. But the angle between the position of the particle at time t and the mean position is theta. This angle is theta. Now what is theta? Now theta is equal to omega t plus phi naught. Right. Now so far we have discussed this case and we have taken theta is equal to omega t, that also represents the phase. Now the displacement is given by the equation y is equal to a sin omega t. But when we take a special case, when we consider time t is equal to 0, observing the simple harmonic motion, the particle is not in mean position, right? Then it has an initial phase, right? Just like, right, for a particle moving along a straight line, right? If the particle is at rest, then initial velocity u is equal to 0 at time t is equal to 0. That we take, initial velocity is equal to 0. But when the particle is not at rest, at time t is equal to 0. For example, we are observing a moving train. Just the moment when we consider the time t is equal to 0, the train is not at rest. It has some initial velocity, right? That is u, right? So in a similar way, right, for a moving train, when we consider, it has initial velocity, non-zero initial velocity at time t is equal to 0. Like this. When we see a train is at rest before moving, then initial velocity is equal to 0. This is that case, right? Now again here, when time t is equal to 0, it has an initial phase and omega t is equal to phi naught, and here phi naught is called, right, initial phase, or it is called epoch, right? So that phi naught is called, right, epoch or initial phase. It is also measured in terms of degree or radian. Now here this particle has a displacement y, and here this has the displacement y. See here, by definition, what is linear displacement? Linear displacement of a particle at any instant of time is the distance of the particle from the mean position. So we cannot take this distance as, if I am perpendicular, as a displacement. No, we cannot take this distance as from here to here as a displacement, because, right, y, the displacement is always distance from the mean position. Therefore, when I consider this distance, right, now I have to consider this angle, right? Now this here, in both the cases, y is equal to a sin theta or y is equal to a sine, right? I will write it here clearly, right? Y is equal to a sine omega t plus phi naught. So here y is equal to a sine omega t plus, in both the cases we have y is equal to a sine omega t plus phi naught, right? So in general, for any displacement equation we can take the general form, right? So when the case is like this, then in this case what is initial phase? Phi naught is equal to 0. Here what is initial phase? Phi naught is equal to 0, right? Because it is at mean position, right? Now when we substitute phi naught is equal to 0 in that equation, then we load the same equation, y is equal to a sine omega t. So when we consider time t is equal to 0, when the particle is at mean position, then epoch or initial phase is 0, then the displacement equation is y is equal to a sine omega t. Suppose when we consider time t is equal to 0, the particle is not in its mean position, then it has an initial phase, right? Then that we have to consider, right? So here, while taking the displacement of the particle, we have to consider this distance as well as this distance, right? Now this omega t plus phi naught, it gives this distance plus this distance, that is equal to y. Is that clear why we are taking, right? So see it, whenever displacement equation is written by y is equal to a sine omega t, it is clear that the initial phase is 0, the particle is at mean position when t is equal to 0. When I take the equation, when we take the equation, y is equal to a sine omega t plus phi naught, that means at time t is equal to 0, the particle is not at its mean position, right? Now we have to consider two distance, initial distance between the mean position and the particle at time t is equal to 0, plus the additional displacement when time t is equal to t, and that is given by this equation. Therefore y is equal to a sine omega t plus phi naught. So when it comes to this case, simply you put phi naught is equal to 0, then we will get the equation y is equal to a sine omega t. Is it clear? Right. Now that completes Now, we will consider another concept, that is velocity of simple harmonic motion represented by V. As we have already discussed, right, a uniform circular motion or any circular motion, rotational motion and simple harmonic motion are associated with two quantities, linear quantity and angular quantity. For example, we have linear displacement y measured in meter, angular displacement omega measured in radian, and angular velocity, right, omega is equal to theta by t, the time rate of change of angular displacement. Here y is a linear quantity measured in meter, theta is an angular quantity measured in radian. Similarly, angular velocity is an angular quantity measured in radian per second. In a similar way, what is this omega? Right, it is theta by t, or it is d theta by dt, where d theta is the small change in, right, angular displacement and dt is the time taken. Now here the displacement changes with respect to time. When the displacement of the particle changes with respect to time, then it has velocity. Here its velocity is dv by dt, where, sorry, dy by dt, where dy is the small change in the displacement of the particle in a time interval, small time interval t. This dy by dt is the time rate of change of linear displacement of a particle executing simple harmonic motion and is called velocity of simple harmonic motion represented by the symbol V. Here V is a linear quantity, not angular quantity, whereas angular velocity omega is an angular quantity, right. Now, the velocity of a particle executing simple harmonic motion at any instant of time is the time rate of change of, right, displacement of the particle at that instant of time, right. That means velocity of simple harmonic motion, right, is equal to time rate of change of displacement. It is the time rate of change of displacement. Now, right, let y be displacement of particle at time t. Then we have equation, displacement equation. Now we have displacement again at time t. It is y is equal to a sin omega t plus phi naught. I have taken general equation, right, where phi naught is the initial phase, right. When initial phase is 0, then we can take phi naught is equal to 0, the equation become y is equal to a sin omega t. Now, velocity of the particle, linear velocity at time t, right, is at time t is y v is equal to dy by dt. Let us take it as equation 1. So the right hand side is a differential equation, right? That is a differentiation of y with respect to time, right? We say that velocity is the derivative of a displacement with respect to time. It is a mathematical term. Now we see here this velocity or this equation can be written as v is equal to d by dt of what is y? A sin omega t plus phi naught. Now we have to differentiate this a sin omega t plus phi naught with respect to t, right? Now after differentiation we get d by dt, right? After differentiating we will get phi is equal to a sin omega t, a cos omega t plus phi naught, because the differentiation of sin theta is equal to cos theta and differentiation of cos theta is equal to minus sin theta. Remember that. Differentiation of sin theta is equal to cos theta. Differentiation of cos theta is equal to minus sin theta. Here, since we are differentiating with respect to time, here we have time t, another term omega t, right? When we differentiate this part omega t, since omega is constant, we get omega here, right? That multiplied by omega. Now v is equal to omega into a cos omega t plus phi naught. This is equation 2, right? This is first expression, basic expression. Then in terms of right omega t and phi naught, right? We get v is equal to right cos omega t. But we have sin square theta plus cos square theta is equal to 1. Therefore, we can write sin theta, sin square theta is equal to 1 minus cos square theta, or sin theta is equal to square root of 1 minus cos square theta, right? Now here we have a cos omega t, right? Therefore this can be written as v is equal to omega a into this cos omega t, or this can be written as cos theta is equal to square root of 1 minus sin square theta, because here we are having cos function. Therefore this cos omega t can be written as square root of 1 minus sin square omega t plus phi naught. Right. Now cos omega t plus phi naught can be written as square root of 1 minus sin square omega t, or this implies v is equal to omega taking a inside the square root. This is equal to a square minus a square sin square omega t plus phi naught. This becomes v is equal to taking a inside the square root, v is equal to omega into square root of a square minus a square sin square omega t, right, plus phi naught. But what is this? A square sin square omega t plus theta, because we have y. So y square is equal to a square sin square omega t. Therefore, v is equal to, right, this omega into square root of, right, a square minus y square, right. This is equation number 3. So we have 3 equations for velocity, right. One, v is equal to dy by dt, v is equal to omega a cos omega t plus phi naught, and v is equal to omega into square root of a square minus y square. Here omega is constant, a is constant for a given simple harmonic motion, but it changes with respect to the displacement. Therefore, velocity is not a uniform or constant velocity, but it is a variable velocity. Velocity varies with respect to, right, distance. Therefore, simple harmonic motion is not at all a uniform motion, right. It is an accelerated motion, right, because velocity changes with respect to time as displacement changes with respect to time. Or according to this equation, right, omega constant, a constant, phi naught is constant, but when the value of t changes, the velocity also changes, right. Therefore, we say that, right, the velocity of a particle executing simple harmonic motion at any instant of time is the time rate of change of displacement of the particle at that instant of time, right. Is that clear? Right, this is linear velocity. This velocity is measured in meter per second, whereas angular velocity is measured in the unit radian per second. Now, so we have velocity at time t, right. Now v is equal to, right, omega into square root of a square minus y square, where, right, omega and a are constants, but y changes with time t. Now, when we take the particle at mean position, so at mean position, what is the displacement? We know that the time t is equal to 0 and the displacement y is equal to 0. Substituting y is equal to 0 in this equation, we get a square minus 0 or square root of a square minus 0, that is square root of a square is equal to a, right. So that velocity, right, is equal to, right, omega into a, right. This is the maximum value of velocity of the particle at mean position. This is 4, right. Velocity of the particle is maximum at mean position. Now at extreme positions, both extreme position in positive side and negative side, y is equal to A. We have taken the magnitude of y, right? Plus or minus indicates that whether it is in positive direction or in negative direction. A, that means, right, this velocity is equal to, when we substitute y is equal to a square minus a square is equal to 0. This is the minimum velocity, right? This is equation 5. So 1, v is equal to dy by dt. 2, v is equal to omega a cos omega t plus phi naught. 3, v is equal to omega into square root of a square minus y square. 4th, maximum velocity at mean position omega a, and minimum velocity is equal to 0 at extreme position. Therefore, when it goes to extreme position, its velocity becomes 0. We will take this example here. A simple pendulum. This is mean position. While executing oscillation, it has one extreme position in positive side and another extreme position in negative side. Now it is oscillating between, right, these 2 points, right, m, right, this is n, m, this is minus a, this is amplitude plus a, right. Now here, this velocity at this point v is maximum, that is equal to omega into a. Here v is equal to 0, here also v is equal to 0. Now here v is equal to omega into square root of, right, a square minus y square. Now this is the displacement y we can take. Now when let us consider the motion at this point. Here it is at rest, momentarily at rest. We see it when we need to set a simple pendulum at rest into oscillation. It has to be slightly pulled apart from its mean position, then released. Before releasing, right, the bob is at rest. So v is 0. When it moves towards the mean position, its velocity goes on increases. And here, the velocity will not become 0. If it would have become 0, then it would have stopped at the mean position, right? But it overshoots the mean position. Why? Because here it gains velocity. Here at this point velocity becomes maximum, therefore it will not stop at the mean position. It will overshoots the mean position and moves in the other direction. Now here, while moving away from the mean position, the velocity goes on decreases and finally at extreme position it becomes 0. Therefore the particle comes to rest momentarily, the direction gets reversed here. Again from here the velocity increases, becomes maximum. Here to here velocity, right, the decreases becomes minimum. So as oscillation continues, right, the velocity keeps on changing with respect to time, and this is an accelerated motion, right? Is that clear? Remember 5 equations. Basically y is equal to dy by dt. Second in terms of cos function, third in terms of displacement, fourth one maximum velocity, and fifth one minimum velocity, right? Now these concepts will help us in finding the kinetic energy of particle executing simple harmonic motion, right? So it is clear that now the simple harmonic motion is an accelerated motion. A simple harmonic motion is an accelerated motion, and if we take an oscillating body as a reference frame, it is a non-inertial frame of reference. We have discussed that in Newton's laws of motion, that is inertial frame of reference and non-inertial frame of reference. Therefore, when we are sitting in that what you call Columbus or something that oscillates in amusement park, or you are sitting in a giant wheel, right, then you feel thrilling. The thrilling is nothing but that you are experiencing a pseudo force, and that is another concept, right? We will discuss when it comes later. Now that's all about here velocity of simple harmonic motion. Here remember we have discussed three important concepts. One, phase of a vibrating particle at any instant of time. Epoch or initial phase difference at time t is equal to 0, and velocity, right, of simple harmonic motion. What is its value at the extreme position and what is its value at mean point. Since simple harmonic motion is an accelerated motion, a particle executing simple harmonic motion possesses an acceleration, right? So in the next class we will discuss, right, acceleration of simple harmonic motion. Obviously, according to Newton's laws of motion, a particle is in accelerated motion means an external unbalanced force is acting on it. Let us also, right, discuss about what is the force that causing acceleration in a particle executing simple harmonic motion, and what is the origin of that force, what is its nature, how does it change, and what is its direction. Okay, I will conclude this class at this stage, right? Remember in this class 3 point, phase of vibrating particle, epoch or initial phase, and the third one, velocity of simple harmonic motion. Okay, thank you students.